Hello everyone, we are Team ManGouard. My name is Cheng, and together with my teammate Chao, we'll be presenting our project for FIT3183 Milestone 3 Champions of the World. Our work focuses on one of the most critical and fast-moving areas in AI, which is deepfake detection. In today's presentation, I'll begin with the motivation and overview of our approach, and then my teammate will demonstrate our results and Google Colab implementation. Why deepfake detection matters. Deepfakes have become increasingly realistic, and that poses a major threat to digital authenticity and public trust. They're now being used in misinformation campaigns, online fraud, and impersonation, not just as harmless entertainment. The real challenge is that most detection models trained on one dataset don't generalize well to new manipulation styles. So we ask ourselves, rather than creating yet another deepfake detector from scratch, can we instead use an existing foundation model and make it more transparent and trustworthy? That brings us to our project goal. Our goal was to explore how a pre-trained multimodal model, specifically OpenAI's CLIP, could be repurposed for explainable deepfake detection and do it without retraining from scratch. We focus on three main objectives: understand how CLIP decides whether an image is real or fake, visualize which parts of the image influence that decision, improve interpretability so that people can actually trust the detector's output. This shifts the focus from raw accuracy to understanding, because explainability is what makes AI responsible. Here's a simplified view of our workflow. We start with an input image, pass it through CLIP's visual encoder, and obtain a deepfake probability. On top of that, we added a visualization layer that produces attention heat maps and occlusion sensitivity maps. Rather than training a new detector, we will leverage CLIP's existing pre-trained capabilities to analyze how it makes its decisions. This allows us to extract insights directly from the model and turn what is normally a black box classifier into an explainable one. So why do these visualizations matter in practice? Let's see. Most deepfake detectors are black boxes. They give you a label like fake, but never explain why. By adding visual interpretability, such as attention and occlusion maps, we can literally see where the model is looking. These visualizations highlight the exact regions, for example around the eyes or mouth, that influence the model's judgment. This not only helps us confirm that the detector is focusing on meaningful facial areas, but also helps researchers identify any potential bias or over-reliance on irrelevant cues. In short, visualization transforms a simple prediction into an evidence-based explanation, which is essential for building trustworthy AI systems. Now that we've covered the motivation and core idea behind our approach, my teammate Zhen will explain how we implemented these visualization methods in our Google Colab notebook and what insights they reveal about CLIP's reasoning.
We base our implementation on the research paper Unlocking the Hidden Potential of CLIP in Generalizable Deepfake Detection. This paper demonstrates that CLIP, a vision language model, can generalize across different deepfake datasets due to its semantic alignment between image and text feature. Instead of retraining or modifying CLIP, we downloaded a pre-trained CLIP deepfake detector from Hugging Face and used it directly in our experiment. Our goal was not to improve its deepfake performance, but rather to understand how it works, how it decides whether an image is real or fake, and what region of the image contribute most to that decision. Our implementation was done entirely in Google Colab. We first ensured all dependencies such as PyTorch, Transformer, and OpenCV were correctly set up, and we loaded the pre-trained CLIP model and processor. Each input image is classified with output such as possibility of real is 0.21, possibility of fake is 0.79, and the source of the image. We then introduced several visualization upgrades to make the model decision-making process more interpretable. The two visualizations are attention rollout, which aggregates self-attention weight to multiple transformer layers to highlight region the model focuses on when classifying. Occlusion sensitivity, where we mask small part of the image and observe how prediction probability changes. This allows us to identify which region most strongly influence the model classification. We also added batch image processing and improved output formatting for readability. Again, no retraining or fine-tuning was done. Our contribution lies on analysis and visualization. Now let's run some images in the Google Colab. We actually are being targeted by another group, Shallow Real, and I asked them to provide some deepfake images to test them out in our deepfake detector. I will put both real and fake images into the Google Colab. Now that it is done running, it will return us P real and P fake along with the image name. We can also run the attention heat map. It will give us an image of where the model is focusing on and overlay this onto the original image. Brighter area is where the model is focusing on. The background has a lot of spots because there are some artifacts or compression. Similarly, running the occlusion sensitivity, it will also give us an image where masking will affect the confidence of the model. In this case, darker area affect the model confidence more, meaning the model rely on this area to detect deepfakes. From our analysis, we found that CLIP focused heavily on facial region, such as the eyes, mouth, and skin texture when distinguishing real and fake images. The attention raw map revealed that the model is sensitive to fine detail and inconsistency that often are noticeable to humans. The occlusion test confirmed that removing these key regions significantly reduced the confidence in classification, showing that CLIP relies on localized semantic cues. Overall, our findings demonstrate that even without retraining, a pre-trained CLIP model can offer powerful insight for deepfake detection when paired with strong interpretability tools. In summary, our project demonstrates a clear defensive approach in adversary AI, using a general-purpose vision-language model to interpret and analyze deepfakes. While we did not modify or enhance the detector, our visualization framework made the model decision-making process transparent, which is crucial for trustworthy AI. We will be posting this presentation video to YouTube as required, along with our final collab submission. Thank you for watching.